Hi everyone, this lesson is going to go over connective tissues, and specifically we're going to go over the various types of connective tissue. So these are the content. We're just going to go over each type of major category of connective tissue, and then these are the various terms that we're going to go over, and yes, that's quite a lot. However, I am going to note that I decided to not go over super in depth all the individual types of cartilage in this lecture. Okay, so these are the major categories of connective tissue. We're going to go over some of the specific types within each of these categories, and we're going to go in this order: connective tissue proper, then fluid connective tissues, then supporting connective tissues. So the first major category of connective tissue is connective tissue propers. So this is a subcategory of connective tissue. I'm going to abbreviate connective tissue with the word or the abbreviation CT. And this is the tissues that basically literally do the connection, attach things, connect things, and tie them all together in your body. And they tend to underlie your skin, your fat, and they also form your ligaments and tendons, etc. And it's tissues that are found all throughout your body. So we're going to cover 3 subcategories of dense connective tissue, then 3 subcategories of loose connective tissue. You don't have to write this portion of your notes down because we're going to cover each subcategory in a table. So first we're going to cover dense connective tissue. These are tissues that have abundant fibers surrounding the cell. And if you forgot, the matrix, the space surrounding the cell and what it contains, is basically as important as the cell itself when it comes to identifying and discussing the function of connective tissues. So in this case, for dense regular tissue, these are tissues that are just lots and lots and lots of fibers, generally parallel fibers all stretched across in one direction, and they've basically formed ligaments and tendons. A different type will be dense irregular tissues, and in this case there is a lot of fibers, but they kind of crisscross. There's a little bit more spacing in it. So generally speaking, dense regular tissue works like a rubber band or a rope, while dense irregular tissues kind of are used as a bed to hold and anchor things down. Your skin, for instance, has a lot more dense irregular tissue, and it usually is a good kind of network for embedding other things inside of it because there's a little bit of space between the random collagen fibers. I'll show you pictures of this later. And then finally, we have dense elastic tissues. These are in areas of the body that you want to be very, very stretchy and very, very easy to change the shape of without losing its toughness and without losing its ability to shrink back down when you don't need it to be widened. Okay, so these are kind of cartoony images of that. So you can see here, because there's dense parallel bands of fibers, there's a lot less space, and what little space you do see, it's a little bit ugly, but there are cells there to help form the fibers, but there's very little space for anything but the fibers and the cells that support those fibers. On the other hand, for dense irregular, because it's kind of crisscrossing everywhere, there's a lot more space to squeeze in stuff like squeeze in a hair follicle, squeeze in a sweat gland, etc. While on the other hand, for dense elastic, there's a little bit more space, but most importantly, there's parallel bands of a rubber band material that's going to let this be extra stretchy rather than just ropey. So you tend to find this tissue in arteries and lungs. Your arteries are the blood vessels that pump blood really quickly through your body, so they're really, really elastic because you need to pump and push large volumes of blood around. So in this case, here are some cartoony images of those same things. So regular dense tends to look like this under a microscope, while irregular or dense irregular tissue, as you can see, it's got the fibers everywhere, but you can see there's all these gaps around, and these gaps are perfect spaces to fit stuff between, like blood vessels and nerves and sweat glands and stuff like that. And now elastic tissue, this is a cartoony image of elastic tissue, but I don't really like the resolution on it, so I found some microscope pictures, and you can see right here these little ripply bands that you see everywhere. That's the elastin fibers that allow that bounce, that allow that stretchiness and return to shape. Okay, so this slide got a little messed up, but we're going to now cover loose connective tissue, which is the most abundant form of connective tissue in the body. the bulk of your body mass is made with with these loose connective tissues. Areolar is a kind of a sticky, loose, membrane-ish looking connective tissue. It's gel-like, but it's got a lot of fibers and it helps anchor things down. So if you ever peeled skin off of a raw chicken and you saw this kind of loosey-goosey, clear band of tissue connecting the skin to the meat, that is actually areolar tissue, and you'll find it all throughout the body. If you ever get a chance to open like a raw animal, when you open a raw chicken, you open a raw turkey, you'll notice inside there's like kind of this loose network, webby, clear network running through all the organs. That's areolar tissue. It's usually the basement membrane. It's around your blood vessels. It's between your muscles. It's anchoring and gluing things down. On the other hand, adipose tissue makes a lot of your body mass, especially right now when we're all at home and not exercising very much, because it is your fat cells. It is the cells that swell up and store all the fat in your body. All right? And finally, we have reticular. Reticular fibers are a little bit harder to state, but they're basically any soft, squishy organs in your body are made of reticular connective tissue. So again, I encourage you to touch raw meat. Honestly, if we were in class right now, I would give you a raw cube of liver. You can. It's things that are kind of solid and jelly, but when you crush it between your fingers, it turns to mush. And generally speaking, you have several organs like that, and unfortunately, they're kind of important organs. Your spleen, your liver, your lymph nodes, they're all made of reticular connective tissue that can squish. So the way it works is reticular connective tissue works by having little ropey webs of fibers running throughout and then anchoring the cells off of those fibers. So that's how it can hold the shape of a very soft, squishy thing together. There's actually tiny microscopic ropes of fiber that's kind of hanging off all the cells like grapes off of it. On the other hand, fat cells tend to look like swollen pools full of clear white stuff, which is basically just fat, and the fat didn't have any dye get into it, so it looks white under a microscope. And then finally, this is kind of a poor image of areolar, but the idea is there's like really loose, webby fibers, and you can see lots of cells throughout it. So let me show you some microscopic pictures of these things. So areolar, you can see there's fibers, and then there's all these like little cells peeking through. This is low resolution, but there's some better resolution pictures in this slideshow. Adipose, again, these big fluffy pools of fat inside, and the little dots you see are actually the nuclei squished to the side of these fat boys. And then over here, like I said, reticular, it's the spider web vines with little grapes hanging off of it. Sometimes I also say it looks like cracked glass a little bit, but reticular, soft, mushy organs are formed through this method. So this is a slightly better image of areolar connective tissue. This is in the index at the end of the slideshow that has all these different microscopic images of connective tissues, but this is a slightly better image where you can see the cells peeking out through lots of fibers running all throughout it. So you can see this is kind of the areolar network with random cells hidden inside this big webbiness of fibers. All right, let's go to the next category of connective tissues. These are called fluid connective tissues. And the thing that makes this connective tissue unique from the other one is it's fluid. It flows, you can pour it into a cup, stuff like that. This is basically blood and lymph. There are cells inside of fluid connective tissues, but the matrix that's surrounding the cells is basically a liquid. Okay, so you have some cells floating inside. They're microscopic, so you can't see them with your naked eye, but if you put it under a microscope, you can see them. There's red blood cells, which help transport oxygen. There's white blood cells that help fight diseases, and there's way less of white blood cells in your blood than red blood cells. And then there's these little spiky partial cells. They're like chunks of cells that are used to help clot your blood in case you start bleeding. They help block bleeding out. It keeps preventing you from bleeding and stuff like that. So In this case, though, the cells are floating around in a liquid background, and that liquid background does have a little bit of fiber to make it thicker, but not enough fiber to make it solid. That's why when blood flows out of your body, it's very liquidy, but then when it dries, it feels a little bit sticky. That stickiness is a little bit of that dried out matrix fluid. When the water evaporates, then you can feel the stickiness of that background medium. So some common fluids, of course, is plasma in your blood. If it's in your lymph, it'll be called lymph fluid. And then there's actually fluid in between your cells called interstitial fluid as well. If you've ever had a cut or a scab or any injury, that as that skin starts to heal, sometimes it weeps a clear fluid. That clear fluid is interstitial fluid. So all the cells in your body have kind of a little bit of liquid bathing it. And sometimes you can see that weeping out of a wound occasionally. So these are cartoony, sort of crappy images of red blood cells, white blood cells, and platelets. These are cartoony versions of the real deal. So this is what they actually look like. So this is a red blood cell, this is a white blood cell, and this is a platelet down here. Okay? But in reality, in terms of the proportion you find under a microscope, if you looked at it under a microscope, there is far more red blood cells compared to white blood cells. So these purple things are white blood cells. And the little dots you see everywhere, these are the platelets. So your blood is mainly all about transporting oxygen, which is why there's way more red blood cells. But looking at it under a microscope, it's very obvious when you're looking at blood tissue. There is lymph tissue, but we generally it's not really observed in microscope labs. I'm not 100% sure why, but we don't really look at it in typical anatomy classes. All right, and then finally the last category of connective tissues is called supporting connective tissues. So these are connective tissues that build up the structure and protective hard features in your body. Generally speaking, it's bone and cartilage. You know what bone is? It's making up your skeleton, and the cartilage is the soft parts of your structure of your body. So like the flexible tip of your nose, your ear, and the cushion that's between your bones are made of cartilage. So both of them provide a really strong framework that support the rest of your body. All your organs and other stuff are, generally speaking, at some point anchored or hanging off of ultimately a bone or a cartilage. If it's not directly hanging off a bone, it's hanging off an organ that's ultimately anchored to a bone, even if it's just through a membrane attached to that bone. All right, so in this strong framework, there's lots and lots of fibers, and generally speaking, there's a large deposit of calcium salts, especially if it's bone, because bone is very hard and solid, so it has a lot of calcium. Cartilage, not as much calcium, though it can gain calcium over time and even potentially turn to bone in some cases. Not always, but sometimes. Okay, so let's go over cartilage as a class. So cartilage is basically a firm gel. It's almost as hard as bone, but it's flexible. Okay, so it's a firm gel containing embedded fibers, and I should also note that it's basically flexible as well. That's why we call it a gel rather than a hard something else. All right, so it's also the only connective tissue that is truly avascular, meaning there is no space for blood flow to get through. There's other tissues that don't have a lot of blood flow, like dense, regular connective tissue, because the fibers are so densely packed. But even those things have a little bit of blood in your tendons and ligaments, which is an example of dense, regular connective tissue. But when you damage your cartilage, it's really hard to repair because there's no direct blood flow through it. So that's why we call it avascular for cartilage. There's no blood supply, which means if you damage it, it takes a really long time for it to repair because it's not getting the nutrients it needs to rebuild and grow and thrive. Okay? Now, the cells that actually help form cartilage are called chondrocytes. So the cells that you see in cartilage are the chondrocytes, and they're dumping out the firm gel and fibers that are forming the matrix that help ultimately build the soft, flexible, but still rigid cartilage that's all throughout your body. Okay? So what happens here is you have your initial cell. So this is a chondrocyte. Okay? That's a chondrocyte. And then the chondrocyte starts dumping fibers around it. So as it's dumping fibers around it, it's kind of creating this little lake around itself. And then so that little pool of fiberiness that's forming around the cell is then called a lacunae, like a lagoon, so it's a lagoon around my chondrocyte. And then what happens is it'll start building and maintaining itself, and then the only way the cell survives and gets enough time to make more matrix is it's going to have to rely on blood vessels that are running nearby but not in the cartilage, and hope some of the materials in the blood diffuses into the cartilage itself. Generally speaking, connective tissues that are avascular, they actually can be replaced if you lose them by corpse tissues, because they take forever to repair. So you can actually get tissue donations from a corpse, like the cartilage from a corpse, and replace the missing cartilage in a person if they have cartilage damage for whatever reason. And because there's barely any blood flow through the cartilage, your body ends up not attacking the white blood. There's no white blood cells to attack that donor cartilage, and you just replace it. It's a little freaky. Okay, and then this picture is of, if you don't understand this drawing, this is of a bone and another bone, and very typically you'll find cartilage kind of hanging out at the ends of the bones. You'll see it when you eat a chicken bone, right? There's that little like white rubbery, not as hard as the rest of the bone on the edges of the chicken bone. That's cartilage. I just realized that the pictures in the slide are messed up, so let me rewrite the words that are missing here. Okay, here's the original slide that's more corrected, so the pictures aren't covering it. So basically, when you look at pictures of a connective tissue, it's going to look like it has weird googly eyes inside of it. It might be in a clear background, it might be in a background full of other fibers, but it's got to have these weird googly eyes. Okay, so these are the main types of cartilage. There's elastic cartilage, fibrocartilage, and hyaline cartilage. For the purposes of this year, I'm not going to really care if you know the difference between all three. I just need you to be able to recognize on site cartilage when it appears. So you should see googly eyes. So hyaline tends to have these bug eye looking things. They tend to look like weird alien eye bulbs. While in fibrocartilage, there's a lot of fiber running throughout, but you can still see these eyeballs inside of it. And with elastic cartilage, the eyeballs are even more eyeball looking, but then you'll see a kind of a webby network running between them. Functionally in your body, if you look at all this cartilage with just your eyeball, it looks all the same. It's all this kind of like white bendy material. But under the microscope, they stain slightly different, and all of them have different presence of fibers, well, with hyaline having the least, and fibrocartilage having the most, and elastic having somewhere in between. However, what you really just need to know is be able to recognize on site whenever there's a chondrocyte or eyeball-looking things, and recognize that those are the things making the background matrix of flexible but strongish material. And likewise, that some of the or all of the cartilage have fibers in it, though sometimes less, sometimes more, depending on how strong and rigid that cartilage has to be. For example, fibrocartilage is found in between the bones of your spine, because your spine has so much impact, it needs a lot of fiber to reinforce itself. But I'm not going to make you distinguish between all three types of cartilage. I just want you to recognize them on site. That's cartilage. Here's cartoony images of cartilage showing the eyeball-looking structures that peek through everything. All right, and now let's go into the last type of supporting connective tissue, which is bone. And we're going to get a lot more into bone when we get to the skeletal unit. But basically, it's just connective tissue that is a lot like cartilage with a cell in the center, or not a cell in the center, but cells in it that drop a lacunae, but the shape that the lake builds around each of these bone building cells kind of makes a unique structure. So in this case, bone, unlike cartilage, it's really hard, and it can be a little bit flexible, especially living bone, but it's hardened and kept really rigid and tough through calcium deposits. But raw bone itself can bend a teensy bit, which is why it doesn't shatter super easily. So it's tough, but it's got enough elasticity when you jump up and down on your bones that it doesn't not immediately snap. Bones that you get in a grave, or really old skeleton bones, those snap because those tissues are dead and they no longer have fiber in it to keep it a little bit flexible. But again, grab that raw chicken bone, see how much you can bend it when it's raw. It will bend a little bit because it's got a little bit of that elastic fiber running throughout. Okay, so the cells itself, instead of being called chondrocytes, they're called osteocytes. Osteo, like osteoporosis, is a term used for anything related to bone. So osteoporosis is a condition where your bones have a lot of holes. Osteo for bone, porosis for pores. Okay? But it's still sitting inside the lacunae. Now, the way the lacunae is shaped is very odd. I can describe how it works, but we're going to do more of a deep dive in it when we talk about the skeleton system. So, long story short, basically it's going to have this kind of shape. Okay? The green stuff is the osteocyte itself. So, let me put in green. So that's the osteocyte, and then it's going to lay down the kind of hardened rings of calcium around each of these bones, and all of these bones typically shape themselves around a central canal that's feeding them lots of blood flow. So unlike cartilage, bone has a lot of blood flow in it to help constantly rebuild your bones and strengthen them. So they have kind of this inside hole that's going to feed a lot of blood vessels through the bones so that it can feed all the cells very efficiently. But basically ends up looking like rings on a tree. All right, so these look like tree rings, and that's how you recognize bone on site. And all those like little black things here, those are osteocytes sitting inside a lacunae. So it's not just a cell, but it's a lagoon, a little hole, and inside that hole sits the cell that's helping to form the bone. So here are more formal images of the different types of cartilage. This is cartilage, this is cartilage, this is cartilage, and where they're found on the body. While this is actually what bone looks like, and just showing you a picture of the bone. Alright, so I'm going to give you some key takeaways. Basically, connective tissue proper is critical for the attachment of organs and protection of your organs. Connective tissue proper tends to be more solid tissues that generally contain a decent amount of fibers, or if they don't have a ton of fibers, they have a decent collection of cells, like adipose cells. Dense connective tissue is really all about the woven, tight, and a lot of fibers, while loose connective tissues are more about having a lot more cells, but it's still solid, and it has enough fibers anchoring things in. Fluid connective tissues, though, have to have fluid because they have that liquid matrix rather than fiber, a really fibrous and solid matrix. And then the very tough, supportive connective tissues that are used to provide rigid structure are the cartilage and bones. And bones are more brittle and stronger because of the calcium, which cartilage does not have. Instead, cartilage is more of a gel that is a little bit more flexible to allow strength through fibers, but to also allow it to be a little bit softer. Okay, so at this point, if you're very tired, you can kind of stop the notes. And the remainder of this video is actually going to be a histological reference walkthrough of all the different microscopic images of connective tissue. So these aren't notes, this is a reference. So the rest of this video is just going to be me walking through a reference. Okay? So I'm just showing you lots and lots of images of dense connective tissues, loose connective tissues, supportive tissues, and liquid connective tissues and all that stuff. So this is dense regular tissue. And it looks like really ropey bands. You're going to sometimes mix this up with skeletal muscle. Be careful. Skeletal muscle will actually look like really thick ropes. So at the same resolution, the same magnification, skeletal muscle, you can actually see the separate bands and ropes running throughout it in parallel. While with dense connective tissue, it just looks like ripples with dense regular connective tissue. And fibrocartilage looks basically like dense regular tissue, but with the eyeballs of cartilage. Okay, dense irregular tissue, I don't know how to describe this. It looks like there's lots of stuff, but like there's ripples, almost like waves, and all this white stuff is just clear space, and that clear space gives a lot of potential for blood vessels and stuff to run through. For instance, this thing right here, it may not look like much to you, but that's actually a blood vessel. Dense elastic tissue, the colors that you're seeing on these images, they're not the real colors of your tissues. They're actually stained. They're dyed pink and purple and sometimes black to help visualize the fibers a little bit more. But in this case, you can really see the ropes running through, and when you can see a single ropey fiber kind of banding up and down over and over and over again, that's elastin. And if you see a lot of them running in parallel, that's how you know it's dense elastic connective tissue. Areolar, which is the first type of loose connective tissue, is really characterized by having thick bands of collagen and thin bands of elastin running throughout. So you see different types of fibers woven throughout, but it looks very clear, more netted space, and you can see a lot of cells inside of it. You can see a lot of cells all woven throughout areolar. And I'm going to be frank, usually areolar tissue, not always, but often when it's stained under a microscope, it's got a kind of pink purple look to them. Okay, so this is a cartoony image of the areolar. I think it makes things a little bit more confusing, but this is the cartoony showing of what all those cells could be. But this is the actual thing of what it looks like in a microscope. And these are more real images of areolar tissue in a microscope. And this is sort of someone's drawing of areolar tissue. That's a slightly better cartoony rendition of the actual microscope image and what all those things could be. This is a special kind of like super high resolution image of areolar tissue. You don't really need to familiarize yourself with this, but you should recognize areolar tissue under a microscope picture like this. Recognize that the thick bands are collagen, the thinner bands are elastin, and all the little circle things are cells. Okay, and this over here is adipose tissue, this lake. That lake inside is containing all fat, lots of lipids inside of it. And when you zoom in on some of the adipose tissue, sometimes you see a black speck squeezed to the edge. That's the nucleus of the cell, but because it's so full of fat, that fat lake pushes the nucleus to the very corner of the cell, so it squishes off to the edge. So you can see nuclei for nucleus of the cells, but the actual fat droplet is what's taking up most of the space of the cell. This is a reticular connective tissue, and this is just showing you what it looks like under the microscope, where it's like all the cells are hanging off like grapes off the vines of reticular fibers. And it looks a little bit like cracked glass because the only way to visualize the reticular fibers, and it's not usually visualized, is you have to use a special stain to make it pop, and it looks really black when you use a special stain. So here are other images of reticular fibers. So it doesn't actually look black in your body. It's just to get it to show up in a microscope, you have to stain it very specially. And then when it does stain, it pops out looking like vines or cracked glass. So now let's go into cartilage. So no matter how it's stained, as long as you see a weird circular eyeball looking thing, the circle being the lacunae, and then the little dot in the center being the chondrocyte, you should be able to recognize cartilage. Even this is elastic cartilage, but as long as you recognize it as cartilage, that's fine for this class. This is another image of elastic cartilage. They're all different colors because of the way they get stained. This is fibrocartilage, again, the eyeball inside the background of fibers. So you may not see it, but there's the eyeballs there. This is hyaline cartilage. You got the weird alien eyeballs there. Hyaline cartilage, weird alien eyeballs. And finally bone, which looks like rings on a tree. And this is many tree trunks all squished together. And you can follow those rings on the tree in that picture right there. And the little circle in the center is just to allow for lots of delivery of blood. All right, that's it. Move on to any other work you have. Bye.